Hello everyone and welcome to this presentation, which is a part of the EAI WiCON 2021 conference. This work, which is entitled SAMA, Security Aware Monitoring Approach for Location Abusing and UAV GPS Spoofing Attacks on Internet of Vehicles, is going to be presented by me, Dr. Babaghayou Messaoud, on behalf of my co-authors listed below. Without further delay, we proceed into its main parts. But before this, the outline is drawn as follows. First, an introduction to the field of study is given, followed by the emerging problematic. Next, the proposed solution, which is called SAMA, is introduced. As a validation, the simulation setup and results is provided after that. Finally, a discussion and conclusion is shown in order to put final remarks and observations. Part 1. The introduction. With the huge advances of nowadays technologies, we are at the point of benefiting from modern vehicles that exploit the promising wireless technologies. From here, a novel paradigm has emerged. We are talking about Internet of Vehicles that are based on sensors and embedded systems. It aims at achieving road safety primarily, provides autonomous vehicles or cars, gives the cars the ability to sense their environment, and allowing the communication with various entities. Here is an illustration that shows the different communications, or also called V2X, which is vehicle to everything, alongside with the different embedded sensors and devices. Now, in order to achieve safety, the vehicle should include its status in a specific kind of packets, the basic safety message, or BSM. The general idea is to use a GPS device to get its position, plus an onboard unit or OBU in order to send the generated BSM packet, which has as a format the following: a source address, often used as a pseudonym, the position and speed of the vehicle, and a timestamp plus signature field for the authentication. This packet is broadcasted from 1 to 10 times per second, has a transmission range of about 300 meters, and contains data like the identifier, location, velocity, etc. With this setup, all vehicles will be aware of each one's position and status, and hence can react accordingly. Safety problem almost solved. Moving now to the second part, the problematic. Noting that we are dealing with location data, and these data can be manipulated even with data integrity. This leads to wrong suppositions. It lets vehicles act wrongly, and in the worst cases, it leads to casualties and accidents. Let's see this scenario. We have an attacker and a controlled or manipulated car. The attacker can influence it with the help of a UAV, which acts as a bridge to control the car. Once again, here is our model. We have the network model with V2V, V2I, and V2X communications. Here comes the attacker, spreading his UAV network at the aim of controlling his malicious cars in order to send a falsified location, which is against safety principles. With the problematic being set, we proceed into explaining our proposed solution that we called SAMA. Before diving into SAMA, the triangulation technique has to be explained. It exploits the signal strength, uses simple mathematical formulas to calculate the position, It gives an acceptable estimation of the locations based on the received signal strength indicator or RSSI, which implies finding a distance from an obtained RSSI, and it was already used in wireless transmission fields. This illustration shows the different possible scenarios: whether no data is received or eavesdropped, a simple reception, a DU reception, or a successful triangulation, which helps them to estimate the sender's location. With this in mind, and continuing from our scenario, the integration of the transmission technique or the triangulation technique via SAMA consists of implementing security monitoring stations. They work in the monitoring layer by collecting messages, calculating the distance, and forwarding the reports. In the other parts, the law enforcement authority with its central module do both of the location processing under the processing layer and the decision making under the decision layer. In another way, and as an abstract, the attacker, the network of vehicles, and the security body are interacting like in the following illustration. Vehicles are communicating normally with each other and use the available infrastructure, but the attacker can still be harmful, since he can forge falsified location with his malicious network of controlled cars and UAVs. Here comes the necessity of the security body, which acts as the defender. This defender entity and can protect users' safety significantly. Generally speaking, the law enforcement authority works with different authorities. As an example, it can work with the certificate authority or CA in order to be able to match the sender's real identity after checking the corresponding certificate used to send that message. For the implementation, we need at least 3 packets from 3 different monitoring stations, as in the left part of the figure. In the right side, these are the collected locations built upon a map data structure. So, for each vehicle, we have a set of its locations that were gathered by the different monitoring stations. Once a packet is received, the receiving monitoring station applies its message reception algorithm. So it calculates the RSSI of the packet, calculates the estimated distance, and finally sends these reports to the central module. In the other side, the central module exists, and its message reception algorithm is as follows. By receiving a report message, if this message was not received before, a new entry is created using the identifier and the timestamp pair as a key. At the same time, it adds the distance d as a key and the monitoring station identifier as a value in the multimap attached to the first entry. If the message was received before, then it just adds the received message to the multimap belonging to the first received entry. Mathematically speaking, the equations used to do the triangulation task are given as follows. First, the RSSI value is obtained as in the equation number 1. Then, this helps in calculating the distance d. After that, and with the use of the equation system of 3, 4, and 5, we can get the two equations 6 and 7, and that is to get the coordinates of the point or the vehicle. Next, solving the equation system present in 8 results in a one step before the final result, that will be the two equations of x and y present in 11 and 12 respectively, and that is the final result. Part 4, the simulation setup and results. To run the simulation, a set of tools were used. The first one is SOMO, a simulator responsible for the vehicle's movement realistically. The other one is VANES, a network simulator where the packets, transmissions and receptions were simulated. PREXT originally is a privacy extension compatible with VANES, but in this work we modified it in order to implement the monitoring system like the monitoring stations and the central device. For the used environment, we took a portion of Munich city. This map is also included in PREXT. At last, two models for the same environment were used, the obstacles and the obstacles free, which are for the signal propagation. This is the Munich city portion. For the coverage modes, we took 4 different densities: basic, moderate, high and absolute. These modes or these models influence the amount of collected messages per type, mono, duo or triangulation. As the simulation step is given, moving now to the obtained results by taking some metrics. Our first evaluation is the number of received messages with type of reception in the obstacle scenario. The results show that by varying the density mode ascendingly, the reception of messages converges towards triangulations. Also, mono receptions decrease significantly. The second results are for the number of received messages with type of reception, but in an obstacle-free scenario this time. The interpretation of the results is the same as before, but with a faster and bigger convergence. As you remark, this is due to the fact that the signal is received without being affected with potential obstacles. Yet, this is not the case in a real world. The last results are the achieved precision in kind of average, best and worst. And that is for both scenarios, the obstacles and the obstacles free. As shown in the table, the density characteristics were given in terms of density mode, overlapping and number of monitoring stations. In the other side, and by taking only the triangulations, we present the achieved precision for the obstacles and the obstacles free models. Since obstacles do influence the transmitted signal, the obtained results for the obstacle scenario were not so good, and it even failed at getting triangulations in the basic and the moderate modes. With the contrary, very compelling results were obtained for the obstacles free mode, not to mention that triangulations were also possible in the moderate mode. To conclude all of these, a discussion and conclusion was elaborated. In sum, IUV paradigm plays a vital role in nowadays, which is safety. Modifying location fields is a security and safety related issue. The triangulation-based approach, or SAMA, is shown to be a potential solution for this problem. Two scenarios were taken, obstacles and obstacles free. SAMA proven a high location detection precision, especially in the obstacles free scenario. These are some of the important references taken while developing this short presentation. And that is it. Thank you all very much for your attention.